The research proposes a combined volume penalization and selective frequency damping approach for immersed boundary methods, focusing on moving geometries. This extension builds upon previous work on static geometries, aiming to improve the accuracy of the scheme by introducing additional damping inside the solid. The methodology involves volume penalization to impose boundary conditions and selective frequency damping to manage spurious waves. The approach is tested using high-order methods and the Navier-Stokes equations. The key innovation lies in reformulating the selective frequency damping formulation for moving boundaries and introducing new manufactured solutions for numerical convergence testing. The authors aim to merge the numerical advantages of high-order methods with the ease of mesh generation offered by immersed boundary methods, particularly for complex flows involving moving geometries. The proposed method for immersed boundary treatment combines the volume penalization, (VP), and spectral filtering decomposition, (SFD), techniques. In the SFD formulation, the control coefficient chi-f and filter width increment are introduced to drive the solution towards the target low-pass filtered solution Q. The target solution is time-varying, and the approach is applied only inside the solid region, resulting in minimal computation overhead. The method is validated through two test cases using the finite difference, FR, method for spatial discretization. The first test case employs the method of manufactured solutions for moving boundaries, which is a commonly used technique for code verification. The unidimensional advection diffusion problem is considered, with a penalized solution S, x, t, and a mask function chi, x, t, that vary in space and time. The analytical solution and flow domain are designed with user-defined parameters, and the source term Q is determined to produce the solution U. The numerical error is obtained by comparing the residual against 0, and the results are shown in Figure 2. The second test case involves a moving cylinder, where the flow over the cylinder is simulated. The method of manufactured solutions is used to validate the approach for moving objects. The results are presented in Figure 4, which shows the evolution of velocities at two probe points. The combined method is compared with the VP method, and the results demonstrate the efficacy of the proposed approach. The penalization parameter eta is fixed to increment t, and the control parameter of the SFD is set to chi-f equals 1, eta. The filter width increment needs to be large enough to remove all spurious oscillations of the numerical solution. The VP and SFD are only applied inside the geometry, mimicking the effect of solid boundaries, while no treatment is applied to the fluid region. The numerical validation demonstrates the accuracy and robustness of the proposed method for immersed boundary treatment. The results show that the combined method can effectively capture the dynamics of moving boundaries and reduce numerical errors. The approach is suitable for complex fluid structure interaction problems and can be extended to three-dimensional simulations. The paper discusses the extension of an immersed boundary method, which combines volume penalization and selective frequency damping, SFD, to simulate fluid structure interactions involving moving geometries. This method is designed to enhance accuracy in imposing boundary conditions within high-order flux reconstruction schemes. The approach decomposes the numerical solution inside the solid into a predefined movement and an oscillatory part, with the latter being damped by the SFD technique. To validate the method, two test cases are presented. First, a new manufactured solution problem is proposed to demonstrate that the combined method can recover high-order accuracy. The second case involves simulating laminar flow past a moving cylinder at a Reynolds number of 100, showcasing the lock-in phenomenon where the frequency of the lift coefficient locks onto the vortex shedding frequency. In the moving cylinder case, the time evolution of velocity and lift coefficient are compared between standard volume penalization, VP, and the combined VP plus SFD method. The results indicate that the combined approach better captures the boundary conditions and reduces oscillations in the velocity and lift coefficient. Furthermore, the Fourier transform of the lift coefficient confirms the lock-in phenomenon, with the frequency ratio being close to 1. The paper also references previous research in the field of immersed boundary methods, discontinuous Galerkin methods, and eigensolution analysis. The combined VP plus SFD method is shown to be effective in enhancing the accuracy of fluid structure interaction simulations, particularly when dealing with moving geometries. The study concludes that this approach has potential for improving the accuracy of high-order schemes in various applications involving complex geometries and fluid structure interactions. The research paper discusses various numerical methods for simulating fluid and plasma turbulence in complex geometries. It highlights the immersed boundary method, which is particularly useful for confined fluid and plasma turbulence. The authors review several studies, including works by K. Schneider, E. Akervik, and D. Tremblay, among others. These studies focus on numerical simulations of fluid dynamics, plasma physics, and fluid structure interactions. The paper emphasizes the importance of code verification, using methods like the method of manufactured solutions, to ensure the accuracy of numerical simulations. It also explores the use of selective frequency damping for steady solutions of the Navier-Stokes equations. The authors highlight the work of A. Plachek on numerical simulation of an oscillating cylinder in a crossflow, demonstrating the application of these methods in different contexts. The paper's findings are significant for understanding and predicting fluid and plasma behavior in complex geometries, with implications for various fields including engineering, physics, and environmental science.